Greetings or good afternoon, depending on where you are. We are going to look today at radiation. We have seen that when it comes to heat transfer, we have talked about conduction, where we saw those Fourier's laws and so forth. We have talked about convection. We have seen free convection, forced convection, and different circumstances. We've seen the transfer coefficients associated with those processes. Let us today focus on the other mode of heat transfer, that is radiation. And this was a very important method or mode of heat transfer. And when we are dealing with this, we are dealing with the emission of radiation from particular types of bodies. And the common ones are the black and gray bodies. Now, when a radiation impinges on a material, there are three possible scenarios which can emerge. That is when a radiation impinges on the surface of a material, the following can happen. The following can happen when a radiation impinges on the surface of a material. There is a possibility that we can have absorptivity, and this is given by the ratio of the absorption to the incident energy. Can have absorption, that is the ratio of absorbed energy to the total incident energy is absorptivity. And this absorptivity is normally denoted as alpha. In other words, when the radiation impinges on the surface of a material, it can be absorbed. And that ratio of the absorbed energy vis-a-vis or versus the total incident energy will give you the absorptivity. The second case scenario is a situation where we can have transmittance of the radiation through the material. Where we have now the ratio of transmitted energy to that the total incident energy is transmissivity, and that is denoted as alpha, as rho. There's the same notation as we have for density. So there's a possibility that the radiation can be transmitted through that material. So we have seen it can be absorbed, it can be transmitted, and of course the relative ratios of these processes to the total incident energy are what you have referred to as absorptivity and transmissivity. Or it can be reflected from that surface. That's reflection. Therefore, the ratio of the reflected energy to that of the total incident energy is reflectivity. plus rho. This is tau, 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 tau. That is tau. So that ratio of reflected energy to the total incident energy, in that case, that will be reflectivity. And so it is very important to take note of these particular processes which can take place when the radiation interacts with the surface, when the radiated emission interacts with the surface. Now, there must be fundamental laws guiding this type of heat transfer, just like we have seen with the convection processes, just like we have seen with the conduction processes. So even radiation, there must be laws dealing with these emissions from these particular surfaces. And so we have what is called the black body. So when we have this particular process where the radiation impinges on the surface of the material, we have seen that we can have reflectivity, we can have transmissivity, and we can have absorptivity. So that in general, rho plus tau plus alpha is normally 1.00. 1.00. In most materials, practically used materials, normally there's no transmissivity at all. So that in most materials used for important material processes, transmissivity is always 0. Note that in most applied materials, tau is equals to 0. Therefore, you can always assume that rho plus alpha will be equal to 1 in those particular cases. Now, a black body or a black surface is one which absorbs, the absorbed energy equals the total incident energy. In other words, it totally absorbs the radiation impinging on the surface. In the black body, the ratio of absorbed energy to the total incident energy, the total is 1 unit. So in other words, it absorbs every radiation which impinges on its surface. Now, and so in general, you will find that when the radiation is absorbed by a surface, there will be increase in the molecular energy within that particular system. And that increase in molecular energy, or that increase in motions involving the molecules, will basically, remember the kinetic theory where we have the increased movement of molecules, then this will translate into an increase in temperature. And in general, it is true that for the absorbed radiation, you will find that there is a relationship between the absorbed radiation and the temperature of the material, and this is given by what we call the Stefan-Boltzmann's law, where that heat absorbed by that body is proportional to the absolute temperature raised to the 4th power. In general, when radiation is absorbed by a material, is a black body, there will be increase in molecular interactions, leading to an increase in absolute temperature. So in most cases, this is the basis of Stefan Boltzmann law, where Q, black body, is sigma T to the power 4, where they absorbed it is directly proportional the change in absolute temperature raised to power 4. And that sigma there is the Stefan Boltzmann constant. Stefan Boltzmann constant. Sigma is the Stefan Boltzmann So let us think about the spatial distribution of these energies. Let us take the example of a hemisphere to illustrate this process. So let's look at spatial. We consider an hemisphere. And let's say the radius r. Let's use that to illustrate these spatial distributions of the energies. So let us have a hemisphere. The radius is r. Try to do it as best as we can. And let us say we have an element here, dA. We have another element here, dA1. So we have another element here, dA2. They are not drawn to proportion. They are not drawn to scale. So it's just for illustration purposes that you have this sphere whose radius is r, and you have this element, area element A, dA, area element dA1, dA2, and let us say that this area element dA1 is on the normal to the area element dA, and the area element dA2 is some angle phi from that normal to the D element dA. This is the upside down. Assume we have an area element dA and dA1 is an area element on a normal to dA, and dA2 is on line displaced angle phi from the normal. So this is just a sphere. We are saying radius is r. We are looking at the area elements dA1, and we are looking at dA2, and dA1 is on a normal to this dA, and dA2 is displaced by an angle phi from that normal. Now, that's important for us to note. Now, the angle subtended by the area element dA1 on dA, the angle subtended by dA1 on dA is given by the angle given by dA1 over r squared. Similarly, the angle subtended by the area element dA2 on dA will be given by dA2 over r squared. So the angle subtended by dA2 on dA is dW phi equals to dA2 over r squared. And of course, the angle subtended by the total hemisphere there on A angle subtended by the hemisphere on A, that angle will be given by 2 pi r squared for r squared, and that is 2 pi. 2 pi. So we normally call it sterads. Just remembering that for a cycle, we talk of radians. So we just call it steradian. Now, it is important for us to take note of these quantities. Now, the rate of energy which flows through dA and flows through dB is basically based on Fourier's law. The framework is the Fourier's law. So the total, the energy, the rate of energy flow through dA1 is dq, it's the black body, and we have n, and that is q b dA, that is qb dA, and that is very, very important for us to note. And similarly, the rate of heat flow through dA2 the rate of heat flow through dA1 will be QB times A1, and the other one is QB to dA2. And in general, these rates of heat flow, dQ, dN, will be given by the intensity of the radiation along that line, that normal, times the angle subtended dA. Now, we have talked about intensity. When you talk about intensity and radiation, that becomes a very important concept. A very important concept. It is important to note the following: that the emitted radiation does not have a uniform intensity in all directions. The intensity is non-uniform. But note that for an emitted radiation, the intensity is not uniform in all directions. That's a very important concept to note. And in addition, the emitted radiation, while it has magnetic waves, even though it has electromagnetic waves, these waves, the distribution of energy is not uniform in these waves. They are of different wavelengths. Remember, those electromagnetic radiations are of different wavelengths. So the energy distribution is not uniform in those wavelengths. It could be uniform in some range, and in some range it is different. So very important also to note that the electromagnetic radiation does not have energy distributed uniformly in all the wavelengths. Very important. Those are two important observations. Intensity of these emitted radiations not uniform in all directions. Two, the electromagnetic waves associated with these radiations, they have different wavelengths, and the energy is not distributed uniformly over those particular wavelengths. So similarly, here, when we move on, dQ, that is through dA2, phi, B phi, will be the intensity along that line which is displaced by angle phi. Of course, this is N phi dA. Remember, these were the angles subtended by the element dA1 on dA, angle subtended by element dA2 with the element dA2 on the area element dA. Very important for us to note that. And so it is empirical from Lambert's cosine law that when you have this area element dA try to draw it as best as we can. Like I've already said, they are not drawn to scale. These are just for illustration purposes. The intensity here the intensity here will be this line, which is displaced by angle phi, will be the intensity of n times the cosine of that angle. Remember, this cosine, that is cosine. Those are trigonometric notations which I believe you are totally familiar with. So that, therefore, from Lambert's cosine law, the intensity phi equals to In cosine phi. That's very important for us to note. And this is an empirical result. So that we can actually put in that expression for I phi into this system, therefore substituting Lambert's cosine law, we have that dq phi is equals to In cos phi the omega phi dA. So we have just substituted in Lambert's cosine law. So we are continuing with our discussions. So let us stop at that particular point. And don't forget, my name is Professor Duke Orata, and we're continuing with these thermodynamics lectures.